Welcome class. Today we will continue our topics of multiplication rules for probability and random variables.
We will cover multiplication rules and probability. The probability of the intersection of two events is found by multiplying the marginal probability of one event by the conditional probability of the second event. This is the multiplication rule. The conditional probability of event A given event B is the probability of the intersection of A and B divided by the probability of B, assuming the probability of B is not zero. The same applies for the conditional probability of B given A. A note on mutually exclusive events. If A and B are mutually exclusive events, then the probability of their intersection is zero. If the probability of B is not zero, the conditional probability of A given B is zero. Conditional probability can be visualized using a tree diagram, as illustrated in Figure 7.7. We begin the tree diagram with the initial event box labeled Events. The first trial shows the probabilities of events A1 and B1. The diagram is expanded to include the second trial, showing conditional probabilities for events A2 and B2 given A1. The diagram is further expanded to include the conditional probabilities for A2 and B2 given B1, completing the second trial. The outcomes column is added, listing the possible combinations of events from the first and second trials. Finally, the probability column is added. This shows the joint probability for each outcome, calculated using the multiplication rule. Tree diagrams are useful for illustrating the multiplication principle, calculating probabilities for independent events, and relating conditional probabilities to other event probabilities. Let's work through an example. In a college survey, we want to find the probability that a student, selected at random, studies both mathematics and statistics regularly. First, define M as the event a student studies mathematics, and T as the event a student studies statistics. From the problem, the probability of M is 0.5, and the conditional probability of T given M is 0.3. We are looking for the probability of the intersection of T and M, which is the product of the conditional probability of T given M and the probability of M. Substituting the values gives us 0.3 times 0.5, resulting in a probability of 0.15 that a student studies both mathematics and statistics regularly. For example 17, a fair die is thrown, and we know a number less than 6 occurs. We need to find the probability that the number is a multiple of 2. The sample space S for a fair die is the set of numbers from 1 to 6, so the number of elements in S is 6. Let A be the event that the number is less than 6. Set A contains the numbers 1 through 5, so the number of elements in A is 5. Let B be the event that the number is a multiple of 2. Set B contains 2, 4, and 6, so the number of elements in B is 3. The intersection of A and B is the set of elements common to both A and B, which are 2 and 4. The number of elements in the intersection is 2. The problem asks for the conditional probability of B given A, using the formula PBA equals PB intersection A divided by PA. We can rewrite the probability in terms of the number of elements in the respective sets divided by the number of elements in the sample space S. Substituting the known number of elements gives us 2/6 divided by 5/6. This simplifies to 2/5. For example 18, a health club conducted a survey on exercise habits, resulting in the given table showing the number of males and females who regularly exercise or not. We will calculate 4 different probabilities based on the survey data, including joint and conditional probabilities. First, we complete the contingency table by calculating the totals for each row and column. The total number of people surveyed is 600. For Part A, the probability of selecting a male who exercises regularly is the number of males who exercise regularly divided by the total surveyed, which is 180 over 600, or 0.3. For Part B, the probability that a randomly selected person exercises regularly is the total number of people who exercise regularly divided by the total surveyed, which is 390 over 600, or 0.65. Part C asks for the conditional probability that a selected person exercises regularly, given that the person is female. We use the conditional probability formula PYF equals PY intersection F divided by phosphorus monofluoride. Substituting the values from the table, we get 210 over 600 divided by 300 over 600. This simplifies to 210 over 300, or 0.7. For part D, we find the conditional probability that a person does not exercise regularly, given that the person is male. The formula is Pn equals Pn intersection m divided by P of m. Substituting the values from the table yields 120 over 600 divided by 300 over 600. This simplifies to 120 over 300, which is 0.4. Let's consider example 19. A store receives a shipment of 6 smartphones, 4 brand X and 2 brand Y. 2 smartphones are randomly selected for display. We need to find 2 probabilities. First, we define our events. Let X be a brand X smartphone and Y be a brand Y smartphone. We will use a tree diagram to illustrate the selection process of the 2 smartphones. For the first smartphone selection, the probability of selecting brand X, P of X1, is 4 out of 6, and the probability of selecting brand Y, PY1, is 2 out of 6. Now, consider the second selection. If the first was brand X, the conditional probability PX2X1 is 3/5, and PY2X1 is 2/5. If the first smartphone was brand Y, the conditional probability P of X2Y1 is 4/5, and PY2Y1 is 1/5. This completes the probability tree. The possible outcomes are listed on the right, showing the 2 selections for each path. The probability for each outcome is calculated using the multiplication rule for conditional probabilities. For part A, the probability that both smartphones are brand Y is the product of PY1 and PY2Y1, which is 2/6 times 1/5, or 1/15, approximately 0.067. For part B, the probability of at least one brand X smartphone includes 3 outcomes, which can be summed up: P of X1 intersect X2 plus P of X1 intersect Y2 plus P of Y1 intersect X2. Alternatively, using the complement rule, P of at least one X is 1 minus the probability of the complement, PY1 intersect Y2. Substituting the result from part A, we get 1 minus 1/15, which is 14/15, or approximately 0.933. Welcome back. Let's dive right into example 20, which is a fantastic problem that combines everything we've learned so far. In this scenario, a car dealership sells 3 types of cars: sedans, MPVs, and hatchbacks. A mechanic randomly selects a car for a maintenance check. The problem gives us a very important clue about the probabilities. It says selecting a sedan is just as likely as selecting an MPV, but selecting a hatchback is 3 times as likely as selecting an MPV. Next, we are given the maintenance rates: 5% for sedans, 8% for MPV, and 12% for hatchbacks. Our goal is to find the probability of selecting a hatchback, the probability that the selected car needs maintenance, and the conditional probability of selecting a sedan given that it already requires maintenance. Before we calculate anything, this is the perfect time to build a tree diagram. I highly encourage you to pause the video and try drawing it yourself. Let's set it up together. Our first set of branches represents the car types: sedan, MPV, or hatchback. Since sedans and MPV have the same probability, we can assign them both the variable X. Because hatchbacks are 3 times as likely, their branch gets quote 3x. From each car type, we draw a second set of branches for the maintenance status: M for needing maintenance, and M prime for not needing maintenance. We then fill in the given percentages as decimals: 0.05 for sedan maintenance, 0.08 for MPV, and 0.12 for hatchback. By subtracting those from 1, we can easily find the M prime probabilities for each branch. Now let's solve part A. What is the probability of selecting a hatchback? Remember that the sum of all probabilities for the car types must equal 1. So x plus 3x equals 1. This simplifies to 5x equals 1, meaning x equals 1/5. Since the probability of a hatchback is 3x, we multiply 3 by 1/5 to get our answer: 3/5. For part B, we need the total probability that a selected car requires maintenance, or P of M. To find this, we add up the probabilities of all the specific paths that end in M. We take the probability of sedan and maintenance, plus MPV and maintenance, plus hatchback and maintenance. Next, we apply the multiplication rule 1 for dependent event, as shown here. By multiplying along those branches, we get 1/5 times 0.05, plus 1/5 times 0.08, plus 3/5 times 0.12. Add those together, and the total probability is 0.098. For part C, we are looking for a conditional probability, the probability of selecting a sedan, given that the car requires maintenance. We use our conditional probability formula, P of sedan given maintenance, equals the probability of sedan intersecting with maintenance, divided by the total probability of maintenance. We already calculated these numbers. We take our sedan and maintenance path, which is 1/5 times 0.05, and divide it by our total from part B, which is 0.098. This gives us a final answer of 0.102. Now let's introduce multiplication rule 2, which applies specifically to independent events. If events A and B are completely independent, meaning one does not affect the other, the probability of both occurring is simply P of A multiplied by P of B. The rule simply means that, to determine the probability of two independent events, you must find the probability of each event separately and then multiply the results. Let's look at a quick example. Yusri has 4 hats, 2 caps, 1 songkok, and 1 cowboy hat. He also has 5 pairs of shoes, 2 sneakers, 1 loafer, and 2 boots. What is the probability he randomly selects the songkok and the loafers? Because choosing a hat has absolutely no effect on choosing his shoes, these are independent events. We just find the probability of each event separately and multiply them. The probability of the songkok is 1 out of 4. The probability of the loafers is 1 out of 5. 1/4 times 1/5 gives us a final probability of 1 over 20. Let's practice this again with example 21. Kair is making 2 independent decisions, choosing a movie and choosing a restaurant. The probability of a comedy is 1/2, and a horror is 1/2. For restaurants, fast food is 3/8, and fine dining is 5/8. Here we want to find the 3 probabilities as stated in A, B, and C. Now, here is a great opportunity to test your understanding. I want you to pause the video right here. Try to calculate the probability for these 3 scenarios. First, that he watches a comedy and eats fast food. Second, a horror movie and fine dining. And third, a comedy movie and not fast food. Take a moment to work through the math, and hit play when you are ready to check your answers. Alright, let's see how you did. If we want the probability that he watches a comedy and eats fast food, we simply multiply 1/2 by 3/8 to get 3/16. For a horror movie and fine dining, we multiply 1/2 by 5/8, giving us 5/16. And finally, for a comedy movie and not fast food, we multiply the comedy probability, 1/2, by the fine dining probability, 5/8, which again equals 5/16.
Welcome.
Example 22 is a great conceptual check to ensure we know the difference between mutually exclusive and independent events. We are given P of A is 0.2 and P of B is 0.51. We need to find the union, P of A or B, under the 2 conditions as in A and B. For part A, if the events are mutually exclusive, it means they cannot happen at the same time, so their intersection is 0, P of A intersect B equals 0. We just add them together. 0.2 plus 0.51 equals 0.71. For part B, if the events are independent, they can happen at the same time. First, we must find their intersection by multiplying them. 0.2 times 0.51 equals 0.102. Then we use our standard addition rule, P of A plus P of B minus their intersection. So, 0.2 plus 0.51 minus 0.102 gives us a final answer of 0.608. Excellent work today. Before we move on to random variables, I highly recommend you test your skills on exercise 7.2, located on pages 28 through 30. These 10 questions will test your ability to work with independent and mutually exclusive events, extract data from tables, and draw complete tree diagrams. This concludes our review of key probability concepts and techniques, including event types, probability rules, data extraction, and tree diagrams. Next, we will cover random variables and probability distribution functions.